Hey guys, in this video we're going to talk about what is arguably the most difficult type of induction proof, which are induction proofs that involve inequalities. This process seems like made out of fairy dust. There's a middle step which involves the inductive hypothesis and the inductive step, which seems almost like magic, but there's a process, trust me, behind this, and I'm going to teach you how to approach these types of induction proofs in a way that you pretty much always get the exercise correct. There is a lot of judgments before you make these conclusions or make these substitutions or inclusions. We're going to get there, don't worry. However, there's a recipe behind that. So that's what we're going to talk about today. In order to tackle these types of induction proofs, we're going to go through two different examples. This is example number 1. Prove by induction that 2n plus 1 is less than 2 to the n for every positive integer greater than or equal to 3. I'm not going to put the second example right now because I don't want to distract you. I don't want to pollute this canvas, but we're going to go through a second example in a few minutes. But first of all, let's tackle this one. Remember that it doesn't matter which induction proof you're trying to tackle, it always involves 5 steps. Writing P of n, which is the propositional function, proving the base case to be correct, the inductive hypothesis, the inductive step, and lastly, we write the conclusion. It doesn't change for induction proofs with inequalities. So let's start with the first 3. The first 3 steps, they're quite easy in this example. So number 1, the propositional function. We're going to write that 2n plus 1 is less than 2 to the n for all positive integers greater than or equal to 3. Just as a reminder, this is what we're trying to prove. Step number 2, the base case. Notice that we're talking about positive integers greater than or equal to 3. So the base case should be a substitution on the left-hand side and on the right-hand side by 3. N should be substituted by 3. The left-hand side is equal to 2 times 3 plus 1, aka 7. And the right-hand side is equal to 2 cubed, which is equal to 8. Now, given that, well, actually the left-hand side is less than the right-hand side, which is what we're trying to prove. It is related to what we're trying to prove. Therefore, the base case holds. All right, so for the first substitution, the left-hand side is actually less than the right-hand side. That's a good start. Now that the base case is done, we move to the inductive hypothesis, also known as P of k. We're going to assume that 2k plus 1 is less than 2 to the k for some positive integer k greater than or equal to 3. So again, we're assuming that this is true. Now moving on to the 4th step, and remember that this is the step that presents the most difficulty. We are going to write P of k plus 1. We need to get to a point in which we prove that 2 times k plus 1 is less than 2 to the k plus 1. Remember, the only thing that we did was to replace k plus 1 over here and over here. Now, how do we do that? And this is only applied for induction proofs with inequalities. Number 1, you're going to start with P of k and develop from there your P of k plus 1. Number 2, you're going to remember the following diagram. And this is why people call it almost like a magical process. You just make stuff up. It's not about making stuff, well, it is a little bit, but it is with some foundation. Remember this diagram. Whenever you have something, and let me go through it using this laser point. If you have, let's say that this is 3, right? I'm illustrating this. Think about this as the number 3, so 3 little squares. If 3 is greater than or equal to 2, that means that you can also state that 3 is greater than or equal to 1, which means you decrease from the smaller side, or you can say that 4 is greater than or equal to 2, which means that you increase the bigger side. In other words, if you're saying that this is greater than this, That means that if you substitute this bigger thing for something even bigger, you keep the inequality. Or if you substitute the small thing for something even smaller, you keep the inequality. That's pretty much what's summarized in this diagram. As I mentioned, we're going to start with P of k. We know for a fact, because we're assuming that that is true, that 2k plus 1 is less than 2 to the k. And that is true, of course, for integers bigger than or equal to 3. So starting from there, we need to get to here. So the goal is to get here. Now, how do we get to the goal? Once we're done, we're going to get on the left-hand side 2k plus 3. And on the right-hand side, once we're done, we're going to get 2 to the k times 2, which is, of course, the same as 2 to the k plus 1. In order to manufacture this, it is easier if we take care of the power first, meaning we can, or we should, multiply both sides by 2. Now notice that this also doesn't change the inequality. If 6 is bigger than 4, that means that 12 is bigger than 8. We just multiply the whole thing by 2 and nothing's changed. So we have 2 times 2k plus 1 is less than 2 to the k plus 1. Now notice that the right hand side already looks correct. We're done. Now on the left hand side, as opposed to 2k plus 3, what we have is 4k plus 2, which is a problem. It's not 2k plus 3. It's actually 4k plus 2. So what can we do here? And this is exactly where this diagram comes into play. This is exactly where we use this property. If we replace 4k plus 2 by something smaller, given that it's on the smaller side, then we're good. We're not changing the inequality. We can, for example, write 4k as 3k plus k plus 2 to then replace this k, for example, by 1. Why would we replace this k by 1? We know that 1 is less than k. How do we know that? Well, k is a positive integer, which is greater than or equal to 3, so definitely 1 is smaller than k, which means that we have 3k plus 3 on the left-hand side. And I know I could do other substitutions, or I could do this faster. I'm just showing you step by step so you get the correct process, because the next thing will require us to do, the next step will require us to do another substitution. Given that this is right here, and this plus 3 is already here, the last thing that we should do is to break this 3k by 2k plus k plus 3. And knowing that we can replace this k by 0, because 0 is less than k. Remember, k is a positive integer greater than or equal to 3. We can just rewrite this left-hand side as 2k plus 0 plus 3, which, of course, is the same as 2k plus 3. So there we go. 2k plus 3 is less than 2 to the k plus 1. And I know this sounds very random. You will get better with these substitutions as you tackle more and more problems. But do know that behind all that, there's a sophisticated argument, which is you only substitute on the bigger side, bigger things, and you only substitute on the smallest side, smaller things. You gotta make it consistent. And then number 5, the conclusion. This is the easy part, or one of the easy parts, given that p of 3 is true, and p of k plus 1 is true whenever p of k is true for some positive integer k greater than or equal to 3, by the principle of mathematical induction, you can write PMI, that's fine. P of n is true for all positive integer n's greater than or equal to 3. And there you go. This is the first exercise. All right, so let's move to the second example, one that involves factorials and exponentials. You will be questioning once you get to the fourth step, which is the inductive step, whether you should handle the exponential or the factorial first. We're gonna get there, but let's get through the first 3 steps before that. So that involves writing propositional function, going through the base case, and writing the inductive hypothesis. So let's get those easy marks first. our propositional function is n factorial is greater than 2 to the n for all positive integers greater than or equal to 4. This is what we're trying to prove. And we're going to start with the base case, which is a substitution by 4 into n. The left-hand side is equal to 4 factorial, which of course is 4 times 3 times 2 times 1, also known as 24. And the right-hand side is 2 to the 4th, which is 16. Now, given that the left-hand side is actually greater than the right-hand side, as we would like it to be, the base case holds. Now, step number 3, writing the inductive hypothesis. We're pretty much writing the propositional function, but substituting n by k and writing the following sentence after that. Assume this is true for some positive integer k greater than or equal to 4. And right now we move to the inductive step. We started by rewriting our p of k, but substituting k plus 1 into k, which means that we need to get here. We need to prove that k plus 1 factorial is greater than 2 to the k plus 1. Now we know this to be a fact, this to be true, and this is what we're going to use to start the inductive step. So starting from p of k, we know that k factorial is greater than 2 to the k. Now, given that we need to get to here, what needs to happen is that the left-hand side needs to be transformed to k plus 1 factorial as opposed to k factorial, and the right-hand side needs to be transformed to 2 to the k plus 1 as opposed to 2 to the k. So we need to do something with this expression in order to convert it to this. And to do that, we're going to use this property right here. So remember, if you have something bigger than another thing, if you make the bigger thing even bigger, then you're fine. You don't change the inequality. You don't break the inequality. And if you make the smaller one even smaller, that's fine as well. If you multiply everything by a constant, that's fine as well. And it is easier to handle factorials before because they are harder to get. So it's easier if you deal with them first. Meaning, if we're trying to convert k factorial to k plus 1 factorial, you're going to need to multiply both sides by k plus 1. And why is that? Well, k plus 1 times k factorial is equal to k plus 1 factorial. A nice way to remember this property is to use numbers. So if you take, for example, 4 factorial, which is equal to 4 times 3 times 2 times 1, and you multiply this 4 factorial by the next integer, which can be represented by the k plus 1 over here, then what you're doing is creating 5 factorial. 5 times 4 times 3 times 2 times 1. So now that we have the left hand side, we need to do something with the right hand side. Now let's deal with the right hand side. K plus 1 would need to be replaced by 2 in order for this to show up on the right hand side. Now, if we can prove that 2 is less than k plus 1, and why am I saying less? Well, it's on the smaller side right here. Then we can definitely make that substitution. We're taking something that's on the smallest side and making it even smaller. Therefore, and given that 2 is less than k plus 1, and we can say that because we know that k is a positive integer greater than or equal to 4, we can indeed replace it by 2. Remember that you have to show the examiner the reason for your substitution. So this is key. And there you go. We just proved p of k plus 1. Now we just need to write the conclusion and we're done. Given that p of 4 is true and p of k plus 1 is true whenever p of k is true for some positive integer k greater than or equal to 4, then by the principle of mathematical induction, we can state that p of n is true for all positive integer n's greater than or equal to 4. And there you go.